Welcome to this video about the Fibonacci numbers. A series of numbers where you take 0 and 1, add them together, append that result, and you repeat the process. 0 and 1 is 1, 1 plus 1 is 2, 2 plus 3 is 5, 144 plus 233 is 377, and thus forth. We put that in Python, where we begin by issuing verbatim the 0 and 1. Then we, as long as the final number of this series, in this case 1, as long as it's lower than some upper bound, which is our function argument, we add a new number under the rules described. And thus we have a function that calculates the Fibonacci numbers up to the first time this upper bound is breached. And as we see here, we do in fact get a bunch of the Fibonacci numbers. But rather than using a while loop, let's try using a for loop. Fib 4, and we'll put in. Rather than using the for loop in this sort of traditional sense, for blah blah in, we'll instead use a list comprehension. Now of course you'll notice that this here line is the same as what we have up here. So the list comprehension basically says do that thing for whatever in range n, and we'll take away 2 of the n because we started with 0 and 1. Alright, so but anyway, this list here in Python contains only none every time, right? So this is actually not that interesting, but it has computed this function, which has changed in place, changed this out list, so we can return this list. Oh, okay, so 19, I miscounted. Anyway, yeah, as you see, we get the same Fibonacci numbers. Rather than using this sort of Python programming logic, we can also go to the math book, where we find some nice equations here using the golden ratio, and we can try to implement that here in Python. So check this out. We get the golden ratio here, and we have a new function that basically returns this fraction here. We get a sample, and we compare that to these functions we found up here. And let's try, and we see that they're the same except for these floating point errors. Now, here's the real point of this video. What happens in between? What happens from 144 to 233? What does it mean to have half of a, or 3.5 Fibonacci numbers? Let's find out. We'll basically exploit the fact that we can give this x value here, we can give that a fraction, something we can't do up here in our logic. We can't have half of a for loop. No, we can't. That's no good. It has no meaning, but we can easily put in 3.5 or whatever in here. Oh. Alright, so we'll define that, but here's the problem. We are raising this negative number to a power, and now that we are beginning to raise a negative number to a fraction, we will have imaginary numbers pop up, so we'd have to deal with that. But that's fine, we just go to the complex plane. That means we augment this function so that it now outputs a real part as well as an imaginary part. And we again take some numbers here, and we look at the first number now in this resulting list. This is just a check that we do in fact get the same numbers. Now let's plot this in pyplot. So we import pyplot here. We should also use numpy, but for some reason it doesn't work today in Colab, so you know, whatever. We get the first n numbers here between the lower bound, upper bound, and the number of intervals, right? The number of sample points, we could also say. So that is n, is our list, and then we take, for all of these up until n, for each interval, we calculate x and y as being the real and imaginary parts respectively of the Fibonacci number that is on a fraction. And we do some pyplot stuff here, obtaining where we draw these numbers here as well as the whole Fibonacci numbers. The whole Fibonacci numbers will rest entirely on the x-axis, as they do not have an imaginary part. Look at that. Look at this. But because this is the Fibonacci number 0, we index from 0 in the Fibonacci numbers, which is nice, like in Python. But you MATLAB fans out there need not worry, because we will very quickly return to the bad way of indexing, because we have to run through 1 twice. So it comes here once, and it loops around, going through 1 again. And this matches perfectly then with these numbers here, 0, 1, 1, and henceforth. This is all very amusing, but you know, because we're raising this negative number to a power that is also negative, that means that as this number increases, it very quickly becomes insignificant, this part here, and then basically if we take a bigger range, well, we quickly drop to 0. But what happens when we go in the opposite direction? What happens with the negative numbers? What does it mean to have negative numbers 3 out of Fibonacci numbers? Well, it's very easy for us to put in -3 and 3 here. And are you ready for this? Boom. Look at that. It spirals backwards, but going through the same points. I love that so much. Alright, so thank you very much for watching this little Python video. I hope you come away from this knowing that Python is not a scary thing. It doesn't take any setup. You can go straight into Colab on Google here, and you can get going. And you're welcome to come and have a play with this Google this notebook here. I have made it publicly available. And if you are already good at math, you will very quickly become good at Python as well. So thank you very much for watching, and I do hope you find some joy in this beautiful mathematics, as well and that you see Python as a tool that will help you express yourself. So thank you very much for watching, and I hope to see you again in the future. Bye bye.